Floris. Thank you. Thank you. So yeah, exploring CPython bytecode. First, a bit about me. I'm not a Python developer, so I'm not really qualified to do this. So my approach is really not going to be like explaining from the ground up how bytecode works. I'm approaching this from the outside in, as in we all know there's this bytecode files and what's actually inside them. I'll go in and start at the bytecode files, trying to read what's inside them, and from there trying to go backwards to how the Python virtual machine actually ends up executing that bytecode. Other than that, occasionally try to contribute sometimes maintain PSI Python system information, which is a small extension module. I've got quite a few years of experience in Python development. I've been working at Bruynooghe for the past 5 or 6 years or something. So, and now with bytecode. So I'm going to start with, as I kind of said already, starting with bytecode files. Reads what's inside them. And really the main thing is that this is not going to make you better developer than other languages. It's just a waste of time. It's an interesting thought experiment, but unless you really want to go and write your own interpreter or write on Python itself, none of this information is going to be very critical that make it much better. But it's a fun exercise anyway. I enjoyed it. And the examples are going to be Python 3. The difference between Python 2 and Python 3 and bytecode is really quite small. There's a couple of small differences as well. It's very easy to see. You can imagine what each other it's not very difficult other than that. Python is really, it's always called an interpreter, but it's really a compiler and a virtual machine at the same time in one kind of package. Whenever you execute any Python file, it will first compile the source code into the bytecode, which will then transform in bytecode file if it can. The compiler actually uses intermediate HT, which is all the subjects. More about things on the HT thing, which is also quite interesting. Now, once it's got this bytecode, it will execute that in the virtual machine. So the virtual machine always loads precompiled bytecode, and then will execute it in stack frames. This kind of context that gives what bytes execute things. This talk is going to concentrate on the virtual machine part, not really much on the compiler part, and the HT transformation to try to into Windows. This is the only image I'm going to say. Because I'm working at making images, and I even installed this in someone else with permission. But so that's like a graphical overview of what's happened, what happens. So the source file gets transformed to HT. You create code checks which is called bytecode files. And then the interpreter will load those, and we'll execute those using stack frames. And at the end of it, you get running program, which is what we want. I'm going to be working with this small module. It's very trivial. It skips a lot of trickier bits, things that you can do in Python, but it's sufficient to demonstrate how the bytecode works. So it's one function, dot string, some very simple computation, returns a number, pop, that's the number. And then on the module level, it executes that function, prints it off in the screen, not string at the module level as well. it's a very small, yes, it skips a lot of features quite quickly. So, I'm going through wishes, and I'm actually going to write things up during this talk that will be able to execute that little model. It's going to be Python, so it will be slow, without any pointers again. Yeah, it's it's not like Python where they spend 5 years or more developing an amount of things, etc. So it's really pointless exercise, but it's really nice to demonstrate how it all works. Yeah, it will still need Python to run. The compiler part, usually it happens implicit, so you don't notice, you just run the program and CPython will compile your files if it needs to. If you do want to do that explicitly, you can use the file compile module to get to also work on command line. There is another module I think compile, which you can point out directly and compile packages, etc. In general, you don't want to really do this, but unless you're distributing packages or something like that. I'm doing an example on the plan to very going through, and your bytecode will end up in this back hash directory. The reason, and I think earlier version of Python 3 as well as Python 3, you just get quite a CPython next to it. This is quite a recent addition, and it makes it easier to share the same bytecode directly between multiple interpreters, which is something that's useful for distributors like Debian, etc. I think I will show using it. But the good thing is you don't really have to worry where the bytecode goes, because the IPE module in the standard library will tell you. So this fetch from source function, you just give it the source file name, example file name from the one file name. There's a couple of others like you can do reverse and do more function in there. So you don't have to worry about bytecode. Before actually going into it, I obviously to just explain some more these two optimization features that exist. Optimization between votes, because they don't really optimize anything. They modify the bytecode. Firstly, when you start using them, you will end up with other files. This is a bit old. Python is one of the only languages that I know that actually uses a different extension. But anyway, the debug thing that's actually useful. It means you can write some tests or write some extra code in what's done the debug, something like that. So that will evaluate the false when we get optimization. And you'll also skip certain statements, which can also be useful. 902 is it's a way of making the files a bit smaller by skipping block strings. However, you have to watch out because actually, if you're using a block string, you still use it and crash. But that's optimization. Well, so how do you read a PyRC file? Well, in the old days, you would say read source and figure it out. Nowadays, you just look on the internet and put in a question, and someone else has figured it out already. That's a very good article about the structure of PyRC files. And essentially, it's really simple. It's a magic number, a timestamp, and a code object, which is the rest of the file. The magic number is there for Python to know that it's got the right version of PyRC file. So bytecode files and formats changes between major versions of Python, and it just needs to ensure that yes, I'm running the right bytecode file. And if that magic number doesn't match, it's going to recompile the source. Start again. The timestamp is also used because Python always looks at source code first. The timestamp is simply used to check, do I need to recompile my code as a source code change yet or not? And then the code object is actually what we'll be interested in, it turns out. Magic number, 4 bytes. That's in my example bytecode file. That's the magic number that comes out. And you can see events in a directory clone on the line feed. That's not really part of the magic number. That's there to detect corruption when people actually being ASCII mode across Windows units and Mac machines and stuff gets manual up. So that's just protection against that. And then the first part is two bytes. It's encoded at little ending structure on that less than ending symbol. It's little ending short, unsigned short. And the number on my example one comes out with 3,180. It's just a random number, it doesn't matter. The only thing that matters is that it matches. If you really care, you can actually go and look at import.c in the Python source code. There's a big box screen, a big comment, where it lists all the magic numbers they've had and what they've what Python version they've actually to, and sort of what they've changed in the bytecode. So actually, this one that they last changed it and they added a new bytecode into it. This is accessible from inside Python again by the module. Get magic. Only gives you the current magic, but that's really everything you really care about. You just want to ensure that you've got bytecode. Any other bytecode will index from the scan anyway, so you don't mind by it. Timestamp is simply a timestamp. Again, little ending code. The file everything in the bytecode file and Python bytecode files, little ending code. So, yeah, you can unpack those. The example that I'll make a slide from something. So, yeah, it just gives you the value when it's changed. The code object then is actually what you care about. Again, Python stuff is very good at making some through. And it includes this Marshall module. If you read the documentation of it, it will say don't use this because it's not general persistence, etc. Its only real reason is there to be able to run for Python to read and write bytecode. It's insecure, it doesn't check its input, etc. All those things, and that's why you've got the magic number on the front, so that Python can be sort of projects when you go. And the API version, you just call it with the 5 pointer that you've got open. And it will read the rest of the file until it gets to the end of the code object. It will return you the code object. And you need a 5 pointer after the code object. So the entire process of reading bytecode file is something along these lines. So you open the file that you want to make sure in Python to open it, the binary file, not just a text file. You get the magic, you check the magic number is fine, but this is bad science, so you don't use a server because when you use a server for this, you will lose the information, you will lose it when you start using Linux code. So it's short to get into use Linux. You can get timestamp out quite easily. Script modulizations and stuff. And you load the code object. And a normal bytecode file will then be at the end of the file. So then you want to get the code object. But you're going to quickly jump back to the compiler now. Originally said, uses compiler module to create bytecode. There's also directly in code. You don't have to use an external bytecode file. You can just call compile module. Compile built-in function, sorry. It takes just the text source code. It wants to know the file name because it's using tracetext and things like that. The mode, which is one of those execute on a single. The difference between those two modes is that exec is if you want to load the whole module. It will execute the whole module in the next phase module. Evil is for single expressions. And single is where you want to use again. It's a special case of debug, which is used when the interpreter, when you use the interpreter to execute. So it will, after executing the expression, it will actually print what you want to do. The other things, plans is something like which number of future statements you want to use. You know, you can do like the future division and something done to future with statements and things like that. Absolutely important. The flags is black now. Don't inherit is again normally if you leave the defaults for those keyword elements, you'll end up with inheriting everything flags, what future statements are active, and what optimization level we have from the code you're executing from. So those three parameters allow you to customize that if you want to force a certain thing. Opening the source file is actually slightly cheating to that style as well, because you don't really know the encoding. You should really know the encoding. I think in the tokenality module, there's an open function that actually encoding that as well. But onto code objects. The great thing about it is documented. In the language reference, there's a data model section, and that's a very interesting section when you're looking at internal Python. It explains a lot of those. As I already mentioned, I think everything that will get executed first gets compiled into a code object. You know, read-only, so you can't actually modify those at all. You can create new ones if you really want to, but it's slightly complicated. And they're a bunch of CL attributes, basically. So the code object, we go back from reading out policy file. It looks slightly like this with the attributes. So it encodes your read file name in there. It encodes line information. That element tab is a very tight way of encoding which bytecode matches starts at which line name. Details of there are in element tab. In the source code of Python again. It's fairly complicated. It's fine packing. Plans are mostly going to ignore things like what future statements are in use, where the functions are out, etc. You know, we're talking about model. The code object, you see the same, like the same code object is used for modules, for functions, for classes. You know, so it just some attributes are just not used. The name then, the name is normally, if it's a function, it will be name function, in this case, no name. CL names is more interesting. This is an array or tuple, representative tuple here, of the names that are used by this code object. The constants again as well. So in the constants you can see doc string, which stored as a string. You can see the two integers. Also, non is the same constant because it's returned again in the module. And then you can see another code object in there. So code objects will contain other code objects, and that's how you get the function picture. Stat size is something that, because I'm writing my little interpreter here in Python, I don't really care about knowing what stat size would be. CPython likes to know up front what stat size will grow up to, because I presume it can be more efficient. And then the actual bytecode is in the CL underscore code. Actually, it's a long byte string, really. This one, it's not the same. I went to some attributes on the previous one, like the bottom ones here. Similarly, I'm hitting some like file name will be on this as well, of course, etc. So everything below is there. But this one is some function that we had. This one doesn't have any names, which is interesting. It does have constants though. Again, a doc string and two integers that it uses. It tells you the argument count. And it has no keyword on the arguments, because I'm sticking keyword on the arguments for now. there are, and the subclass of free class is, again, I'm going to skip this, but if you've got nested functions, so you've got function A and function to define other function, you can use variables from outside from the parent function. Subclass are basically the parent function saying these variables are going to be used by some functions lower down, free classes and the opposite in the function lower down saying these variables need to come from somewhere higher. And that, yeah, I'm skipping information of those. Number of locals, again, I don't really care about that in CPython likes to pre-allocate stuff like that. Knowing that. And actually, variable names used. That is useful, that will end up in the locals dictionary. Again, stack size and the actual bytecode is a bit short in this case. So, what's in the bytecode? Again, the standard library is great at this. This assembly module, this is very good. It actually documents even all the bytecodes that I used. So you don't even have to go and read source code. It's all right there. And then there's two really useful functions. This will show code, which will very quickly dump your code object. And you just see a nice summary of all those attributes that it has. And this which will tell you what the bytecodes are, what they look like. So, yeah, if I take a function object I have, that's how it shows it, and that's the essential things you want to care about. Yeah, we've gone over these already. And then, actually looking at the bytecode, if you use this with this, just as a reference what the function looks like, here you can start to see what's going to happen. It starts with the function arguments end up being in the locals dictionary of the function by the comma. So you're loading a variable onto the stack. So Python is kind of stack-based virtual machine, so it's got this stack and then it's got this couple of arrays, the variables and the constants. Look there, you look up all the arguments. So maybe I should first tell what the different things are. The numbers on the first line is actually an line numbers in the source code. This one is done with the address of the bytecode, which is just an index into that string, that byte array in the CO code object. Then you've got the name of the bytecode. And then the last column is the attribute, which is always a number as well. But depending on the bytecode, that number means look up something from this constant array, or something from this names array, and between brackets, this assembler does this already for you, so you can nicely see what's happening. And so this one is loading the variable A, it's loading to multiplying those, and then it's storing it again. So it's loading A onto the stack, it's loading 1 onto the stack, and it's multiplying those. Multiplying will pop those to on the stack, and then push the result back onto the stack. And the result of that will just store again into a variable. Same for B and the next more. The next line is the same kind of thing. And then, yeah, and again, it's just looks through it like that. And the end returns the value by pushing it on the stack. So, as I said, these are the bytecode names. They are documented in this module, and it tells you what they do, which I sort of set away. It also says what happened from the stack to the stack, etc. It's very helpful when you're trying to understand what the bytecodes are going to do. So this is where you should really have a nice little picture of how the analytic works with stack and various arrays, but I'm not great at pictures, so I wrote a class instead. And this is my own class implementation of frame kind of thing. Python has frame object, which is kind of was the same, similarly, bytecode, etc. I put the same name as Python does in there, just to make it simple. That is just being space, so a frame of column. Code will actually contain a code object. This frame is going to execute. Last night is the instruction you wanted for the bytecode. So you know there in bytecode, byte array you're working. And then three dictionaries with those locals and built-ins to look up. The last one of those is the stack, which can do a slightly metal, I think, by putting this into the frame. So creating a static frame kind of thing. Usually you have one big stack. And when frames come and go, they just all the same here in the stack kind of thing. It's lots quicker and easier to do it here. And the execute method here is what we're going to do now. And we'll be able to run through the bytecode and actually execute it. So it's a long byte. The actual bytecode itself is a long byte. A long byte array. If you want to read it like more in a better way, it's kind of we convert it into integers, and these are the bytes. They're integer values. So you can sort of see from here that the first bytecode, what was fast, I think, which is 124, 00 is its argument. So arguments consist of two numbers going down combined. Again, little n and code and time. So the next bytecode will be 100, which what number it was. Again, the decimal is really, really useful. It has a list of all the bytecodes. You just get the index and you know its name. And again, it's got mapping the names back to numbers. So it's really nice to have to look into. This model, there's another thing. This will have arguments. It's not currently in its version anyway, not allowed. And that's what you can use to know whether your bytecode takes an argument. So if all bytecodes are larger or equal to 90, will have an argument. All bytecodes that are lower than 90 won't have an argument. Arguments, yeah, 2 bytes living in a different code. So first go at writing an evaluation to evaluate bytecode. So get the actual code in the byte array and just making it short variable. Initializing the instruction pointer, and the actual loop in CPython itself, it's an infinite loop until someone breaks out of it. So it's really easy to break Python and make it sexual by fudging the bytecode if you hand, or if you just chuck random strings into the bytecode if you hand multiple bytecode. It can actually, it's not that hard to make CPython crash, and so that's why bytecode is really a trusted thing. It needs to work, it needs to be correct. I decided to, the actual bytecode side again, in slide build maybe, tired, but it's quicker to just click create these methods onto the same frame object. And you basically loop through some of that slide with get pattern. Loop through all the bytecodes. After you've executed a method, you want to increase the instruction pointer. That depends on whether it's going on or not. There's one code that I'm doing especially here. It's to break out of the loop, and then you go by loop on, which is false. That and then returns that value. Passing arguments is kind of passing arguments is kind of tricky as well. The arguments are they need to, when you compile a function, they need to be passed into, they need to be put into the local dictionary of the new frame that we just created. The code object tells you what your argument count is, but the So I'm checking that in this case I just decided to want the element passed into the basic method here. So I'm checking that they're fine. I'm also, again, I'm also checking that, because I'm not doing the cleaning items for now, I'm also checking that those are not used. And then the position of the arguments is actually important that they get passed into. Because that position, the first argument will be, you will have to look up in this code object again, you've got variable names, and the position, the index of the position will be reused there. So that's what you need because it gets the index position of the argument. And that's where it looks up the name, and that knows that the value it got, or the object it got, needs to go in that name in the local dictionary. So that's the receiving part of passing arguments. Other than that, so we can execute from that. So handling bytecodes. I'm doing them as methods from the frame object here. Just a quick review for this output again. So that's what you've done. The executing. There's the simple ones. Load fast, store fast. We need to look at the arguments or integers. So we need to look up in the right range, in this case, 0 names, and put them from the stack onto the locus dictionary all the way around. Load const needs to look up in the constants array. That's all pretty straightforward. Binary multiply, that's especially most binary operates will work very similar. If you remember the object protocol in Python, basically, multiply is actually implemented or can be implemented in Python again itself. So you need to look at the done operator, which is generally called on the left-hand object with the right-hand one. So that can have a go and return value. If it doesn't return value, if it doesn't know the other object, it doesn't know how to multiply that object, it's just not implemented. And then Python will try the other object and say, do you have a null method? If so, do you know how to multiply yourself with the first object? That's what this loop does. It needs to pop those values of the stack. It needs to and then it just checks whether the null method is the way it calls it. And then at the end, if none of them have to multiply, you get a type error. Otherwise, the result always goes back to the stack. So bytecodes just operate in the stack.
Shouldn't that be armol, the second one?
Okay.
If you're trying the right hand side, then it calls armol, doesn't it?
I'm not sure. I would have to check that. It might be yes. Binary very similar. Actually, almost the same. Just another method. Again, possibly fire as well, I imagine, if it's armable. All the methods exactly the same. It just calls it to object, tries to figure out how to do this after the other one. Return value is actually nothing in this case because we already special case that in the value. So the return value is not going to mean, it doesn't do anything. The return value needs to call the stack and then return that value to the caller. So the tiny VM value that I've been building so far, it can actually execute this method now. With this code, if you create a frame with the code object, or some, you execute it with some parameters, it comes out and that's the right result, executes that entirely. So, time to look at the module. The module is a lot bigger, it doesn't fit on screen. Again, you can see sort of do things you've seen already. loads of docs string here. The modules actually carries the assigned onto block explicitly functions going out and into the function object. Then on line 4 it gets more interesting. It loads this, again, loads of constant, which is code object in this case, and it calls this make function thing. A make function is actually where it's going to take that code object and create a function object out of it. It will then take that function object and store it into another variable. It's using store name now instead of store class. There's something different there. Similarly, the next line is line 11. That was the if statement, if name equals name. So the if statement load name, load columns, both of those will end up putting something on the stack. So now you've got 2 new items on the stack. Compare will take those 2 items on the stack, do the comparison, and put the result back onto the stack. Next is the actual if time statement. It takes top of the stack again, and if it's tests whether it's false or not. If it's false, it will do an absolute jump. The number of K49 is actually the address in the bytecode array again, so it's the address of the bytecode, the next bytecode that you want to execute. And I think it's looking at this like this. So the last is duplicating slide of it. So now if it's not jumping past this, so this double arrow bits, the double arrow bits is the jump label like those two, which is something else like this, gives you now, what we see doing now is especially those 2 names again, which is print and sum, which is 2 functions. So they'll be popped onto the stack, 2 function objects. Then it will put 2 constants in, the 2 integers there, 15 and 4. But again, pop those on the stack on top of the function object, and then it will call the function. So that's how parameters are passed to the function. That'll pop put onto the stack, and then that call function will pop those on top of the stack and get them to the new frame in the correct way. You can see now nested calls as well. So a call function will then push back on the stack the result of the function call. And the next function will have that as its argument. And you pop that on the stack again to execute. Call function will end up removing because the function is still on the stack, so it will end up removing the function off the stack too. There's a jump forward there. That's a relative jump. I'm not entirely sure why I can put that in there, because it's just moving to the next bytecode, it's actually not doing anything. Jump forward 0. At the end, yeah, load constant, loads are not going to return bits, so that's what we want to kind of returns. So the new bytecodes, store name, that's pretty straightforward. You just get stored into the local dictionary again. You need to look up the name in the right array again to see the name in this case. Load name is and this is why you can see why we have a load faster earlier. Load name needs to actually check where the name comes from. It starts with the locus dictionary. It's not in the locus, it will start with the private locus. It's not in the globals, it will have built in. And that's why load fast was kind of because the compiler sometimes kind of knows that you're being locals. And if in that case we put load fast in there, so it doesn't have to do all those because it's a lot of when doesn't it know?
Why do you have to?
There's a load fast, there's a load working as well. So sometimes it's fine, there's a load name.
What's the example where name is the
you can have a variable on the side that equals the float of the program.
If you use a global, like you know the global statement in the function, so if you use that, you know it needs to go to global. But if not, you haven't used the variable yet, so you can just go outside. Name our regular time. Put the log back on the stack. Next motion then. But yeah, this one doesn't handle import values, doesn't handle keyboard elements either, keyboard only elements. But basically, it pops the function. It pops the function object of the stack, and then it will from that it will create a function object. So yeah, from the code object or stack, so again, create a function object from it. I could have defined my own function object, but the BICE module in Python lets you create new function objects from scratch by function type. All it needs is the code object, which I just brought on the stack, and globals dictionary. Puts that back on the stack, and now you've got function objects around this will probably be stored environment next. Function objects have a couple of attributes that you might have. The code object is referenced in there. You've got quick access to the module, access to module, etc. So you don't have to go via code object to find those things. Its counterpart, card function, is more interesting. So again, not handling the whole value of keyword only arguments. Its argument of that bytecode gets actually split into it, treats it as two separate numbers each byte. And one of them is the number of arguments, which includes the ones with the default value. The other is the keywords arguments. I think that's keywords only arguments. So yeah, you have to split. It decomposes that again by shifting and together. Again, I'm skipping keyword elements. And then the next thing it needs to do is, for each argument, it needs to look through, needs to pop the arguments from the stack. In this case, they're just position arguments, and they'll be on the stack in the right position. Keyword arguments would be as the key name and then the value name of the stack. And they need to be popped in the right order. So I'm popping them all on the stack. You need to revert them to pass them on to my function. And then the next thing is you need to differentiate user functions and built-in functions. So I'm checking, basically built-in functions won't have a code attribute. So I'm checking whether it's a user function using that attribute. If it is, I know I can create a frame again, which I'm using to execute it. Passing the right, passing the verb and code, and the code object needs to create a frame for, and then execute it with the arguments. If it's a built-in function, I just call it directly, prints in the built-in function, so I have to put that special case in. Well, built-in code will do explicit. Do the right thing. The return value of calling that function needs to be respected in the stack. I think I've said this already. So, yeah, the thing that you can, the number of arguments, the thing that you learn from that actually is the number of arguments you can have maximum 255 arguments passed into a function because of that bytecode. How that bytecode argument is used. Hidden limitations somewhere. Object is false. Pretty straightforward. You need to change the target, the instruction pointer with the target. I'm doing -3 because I know that the value will actually happen straight after this function returns. Which, the value just that's true. Jump forward. It's very straightforward. Just update the instruction pointer. Pop stack is just discarding the argument. We don't care about the return value of the function. Right? We don't care about the return value of the print. That's why we got top in there. So executing the entire module then. We see the first part, we get the code object. Next is frame function, that whole frame functionality is actually able of compiling, creating that whole, executing that whole code effect, and it brings out the result, which is all very good. This is very complete. Obviously, I've mentioned most of the limitations, but in fact it gives you an idea of how the bytecode works, how you can use those bytecodes, what you can build to do. And one of the things I did was a standardized bytecode. If you don't have some bytecode that adds extra information onto if the arguments, because you're limited to about 16 arguments. Sorry? Yeah, it's unlikely because it's all the things you're looking at business arguments, they go into the array of file names, array of names, constantly. It's unlikely to have more than that number. Yeah, I'm supposed to talk about. I think there's like a very big thing of what people have gone wrong with bytecodes, where you can also do this. There's a couple of models that are often making and craft bytecode if you want. People have managed to do go-to, some people. Actually, this is actually slightly useful. This is called a coverage package. By changing libraries, we managed to get more coverage out of it. Decompiling obfuscation. Obfuscation is quite bad because you can't read trace backs anymore, so it's not very heavy. Yeah, and I think I mentioned some quite old things in this talk. Earlier this week, the switch statement has been implemented as well. And yeah, that's it, I think.
So there is room for some questions or interaction. You can pass the microphone beyond you.
Maybe a silly question, but why do you need always to use the underscore methods? For example, when you multiply, you do underscore move, and then instead of just using the multiply operator.
That's the way Python multiplying is implemented as a protocol. So if you create your own class, you can define that method that is going to go move. And that's the protocol that Python uses to multiply. So it means you can override multiplication and things like that. And the way of looking at that middle method, passing in the other items, instead of just using multiply. I could have done that directly in because I'm just getting that in the very end. That's how the Python protocol comes up.
Because I mean, when you check the move and do all the things in the binary multiply, binary multiply function, you could just do a multiplication and then the exception is raised automatically by Python if the move is not on. So there was just one line instead of all the things.
Yeah, I just wanted to show what if I could have put in a multiplication of two objects, you would have had the same result. I just wanted to show that how you would actually have to do it.
Okay, so first of all, you do need the rmul and radd and all those. That's used if you for the right-hand side. So consider division, where 3 divided by 5 is very different from 5 divided by 3, or multiplication with a string and an integer. The other thing was there was a question about global, and so I wanted to say very quickly exactly how global works. When CPython generates the bytecode for something, all locals are stored in the local stationary, and then there's a post-processing step after the compilation of a function that scans over and looks for assignments. Whenever it finds an assignment, it says, aha, this can be a load fast, and it converts all the references to that variable into load fast, store fast. So that's why whenever you assign something inside of a function, it occludes the global that matches that. So you have to, in order to be able to assign to a global, you have to say global, and then Python treat to non-local as well.
So, any more questions? Nobody? Okay. Thank you, Dan.